In this paper, a mechanical processor is designed to offload repetitive subtasks associated with locomotion from a conventional computer actuator sensor setup to automatic mechanical processes. Migrating processing out of the computer reduces the number of transduction steps, allows for fast responses to dynamic events, and enables a high-powered leg reflex triggered by ground contact. Here we show the two robots tested in this work. On the left is a conventional computer actuator sensor setup, and on the right is a robot with subtask logic programmed into a mechanical processor. The robot on the left receives high-level signals from a computer, which communicates with the motor drive board to command a brushless motor. A motor encoder and current sensor are used for commutation of the brushless DC. The motor is connected to a spring forming a series elastic actuator, which is subsequently connected to the leg mechanism, which manipulates a foot that interacts with the environment. Installed on the leg is an encoder that sends digital signals back to the computer. Using this feedback, program logic on the computer implements position control and contact detection with the environment. This is the conventional way to go about things. On the right side implements similar program logic, but on a mechanical processor. At the top, we once again start with a computer capable of high-level logic. Although for this illustration, the computer only sends a constant signal to the brushless DC driver. With just this signal, the mechanical processor performs an appropriate position control loop and automatically detects and reacts to ground contact. This is performed without digital signals flowing to the computer processor, but rather mechanical signals, that is, energy, position, and force, flowing through the mechanical processor. A kinematic singularity mediates these mechanical signals, dictating actions of the motor and leg based on a combination of component states. Unlike digital signals, some of these mechanical signals take on relatively large magnitudes and can be directly used to perform useful work themselves. For example, a kinematic singularity inhibiting motion leads to torque buildup in the series elastic element, indicating the position set point has been reached. These large torques lead to spring deflection, forming an elastic energy reservoir that can be slowly charged while out of contact with the ground, and rapidly released immediately after contact is detected to push off the ground, forming a new functionality executed by the spring charging control loop, labeled in this diagram. This third subtask is not possible by the robot on the left. That is, unless a clutch and a contact sensor are installed downstream. When the robot is out of contact with the ground, a clutch can engage to fix the distal end of the series elastic element, allowing it to be charged by the motor. Then when the contact sensor activates, the clutch can open to release this energy into a push-on motion. The immediacy of this reaction would be limited by the latency of digital communication, which can be a bottleneck for cost-effective electronics. On the other end of the spectrum, the mechanical processor by itself would not require extra mechanical to digital transduction steps, nor extra actuators or sensors, not even a high-level computer. In its simplest form, by connecting a brushed motor to a battery, all three subtasks would unfold, that is, leg position control, contact detection, and spring charging, with nearly instant reaction times. Of course, without a head computer, the device will be unable to stop and start or regulate its height. The device perspective in the end is to consider blends of computational and mechanical processing. Whereas the computer processor addresses high-level coordination and mechanical processor focuses on low-level repetitive fast dynamics. On the left, we demonstrate a conventional computer actuator sensor system. Under constant commanded motor torque, the leg moves smoothly through its motion but performs no subtask logic. With motor position control and the contact detection implemented, the computer processor sets the leg at its ready position and awaits environmental contact. On the right, under constant commanded motor torque, the mechanical processor sets the leg at its ready position and awaits environmental contact. The stroke of the two legs is the same. The two robots were compared by hopping on a table using a pitch-constrained planarizing boom. A boundary was only used for later experiments to artificially vary gravity constants. Each robot weighed approximately the same and was powered by the same gear motor, a 75-gram Maxon ECX13L. The effect of spring charging loop is pronounced in the resulting center of mass trajectories. The robot on the left detects ground contact through a spike in the encoder readings, then immediately commands the motor to push off at full power. The robot on the right mediates the interaction between spring energy, leg position, and ground force through its mechanical processor, using essentially no motor control. Running the left robot with no motor control exhibit similar energetic performance. Slow motion further revealed the inner working of the mechanical processor. Note that the thin green flags are attached to either side of the spring to show its deflection, while not in contact with the ground. The motor and leg advance to set the leg in its ready position in preparation for contact. This is enabled by placing a kinematic singularity at the ready position. With the series elastic actuator pushing against this singularity, the leg no longer advances, but instead the elastic element experiences large deflection, resulting in energy storage. Each hop cycle lasts 400 milliseconds, with only 40 milliseconds spent in contact. Auto-contact spring charging allows ample time for a small motor to add energy to the system. Upon contact, this energy is automatically released due to the pre-programmed directionality of the kinematic singularity, which was set up so that vertical ground reaction forces easily advance the mechanism into its push-off motion, simultaneously releasing the stored spring energy for a burst of power triggered by ground contact. After this step, the cycle immediately repeats with no need to reverse the motor or control it at all. The robot repeats this spring charging cycle about 2.5 times per second. Slow motion footage reveals the inner workings of a computer processor, shows negligible torsion spring deflection, while it performs subtask logic of leg position control and contact detection. Motor and leg act together, and spring charging does not happen when auto contact. The kinematic singularity is apparent in the leg mechanism. When lines along its three binary links, the black links share a common intersection. Nearness to singularity can be visualized by the area of a cyan triangle bounded by these three lines. A small area indicates it's nearly singular, and from a practical point of view, being near or at a singularity are the same. Note that the cyan triangle remains small over the entirety of mechanism's upstroke, rather than just instantaneously. Over the near singular region, the mechanism gains extra mobility, allowing the foot point to travel upwards, despite the input link being fixed. This extra mobility over upstroke enables automatic contact detection and reaction as vertical ground forces move the mechanism out of the singular region. Upon entering the near singular region, series elastic torque has no authority over the leg motion, meaning once it arrives, it's come to a stop, which is used to set the leg at its ready position while auto contact. Despite the leg not moving, the motor will continue to move, as the two are coupled by a spring, enabling auto contact spring charging. The cycle is further illustrated by dynamic simulation. The thick green arc is a visualization of series elastic spring deflection, and the magnitude of the motor torque and vertical ground reactions are visualized as generalized force vectors pushing on the mechanism constrained configuration space. In real time, the mechanism's motion is essentially invisible. In the absence of an input singularity, motor control regulates the positioning of the leg to create a periodic hop, but dynamic energy storage is greatly reduced. In the absence of input singularity and motor control, the foot might contact the ground in unplanned configurations, but is still more or less periodic. Thank you for watching.